All right, welcome back, everyone. In this lesson, we're going to talk about exponential growth and decay. This is section 5.6. All right, everyone, so in this section, we're going to talk about exponential growth and decay. And we're specifically going to talk about exponential growth in terms of population growth, in terms of interest compounded continuously. And then we're going to talk a little bit about doubling time and half-life. And then at the end, we'll talk about limited growth. So an exponential growth or decay function can be used to model real-life data to determine what's possibly going to happen in the future. So for example, if your interest in a bank account compounds continuously, so it's always rolling over and you're always getting more and more money, or if we're talking about the population growth of some city or a state or a country, all of these things can be modeled using an exponential function. The basic exponential growth function is what you see there. P of t is equal to P0 times e to the kt. In this equation, P of t represents the amount at a future time, so how much money do you have in the future, right? What's the population at a future time? P0 is the initial amount, so how much money did you invest or how many people did you start off with? K is known as the growth or the decay rate. If K is positive, then the number is growing, it's getting bigger. If K is negative, then the number is getting smaller, it's decaying. And T is the time, usually in years, but depending on the problem, it could be measured in different units. When you're given K in the problem, it'll almost always be given as a percent, just like we did before with compound interest problems. Be sure to convert it to a decimal. And when you're given information about initial conditions, it's possible then to determine the value at some future point. So let's try this. In 2009, the world population was 6.8 billion. The exponential growth rate was 1.13% per year. So first we want to find the exponential growth function. This just means write down what we know and plug in what we know. So our generalized equation, P of t, is equal to P0 e to the kt. And so to write the growth function, we're just going to write P of t. Okay. Our initial amount is 6.8 billion. Because everything we're dealing with is in billions, and we can just drop off the word and keep 6.8. That's our initial amount. And we'll add the billion on whenever we find our answers. And then that's E. In this case, it says K is a growth rate, so that means K is positive. And it's 1.13%, which is 0.0113 as a decimal. So that's e to the 0.0113 times t. That would be our exponential growth function. Now we want to estimate the population of the world in 2015. So first we need to find t. Well, in this case, t is 2015 minus 2009. And so we just get t is equal to 6. To determine the population in 2015, we're just going to plug in t equals 6. And so that should give us 6.8 e to the 0.0678. And when we plug all of that in the calculator, you get the population in 2015 is equal to 7.3 billion. Now, the last part asks, when will the world population be 8 billion? So let's go to the next slide. And we want to know, when is P of t equal to 8, or 8 billion? Our equation, 6.8 e to the 0.0113 times t. And now we know P of t is going to be 8 or 8 billion. And so we're just going to substitute that. And solve the exponential. Right now it's just solving an exponential equation. We want to isolate the exponential, so divide both sides by 6.8. From there we're going to get e to the 0.0113 times t. 8 divided by 6.8 gives 1.1765. Then, just like with every other exponential equation, we're going to take the natural log of both sides. The natural log of the left-hand side is just going to give us 0.1625. The natural log of e to the 0.0113t, right? Remember, the natural log of e to the x is just x. So the natural log of e raised to any power is just going to give you the power. And since we're looking for t, now we just divide. And so we find that it's going to be 14.4 years after 2009. .4 years after 2009. 14 years from 2009 would be 2023. And so we would say it's going to happen in 2024. Right, because 14 years is not enough. We need that extra 0.4. So 14 would put us to 2023. And that extra 0.4 puts us over to the next year. Now let's try a very similar thing, except with compound interest. So suppose that $15,000 is invested at an interest rate of 5.4% per year, compounded continuously. When we compound interest continuously, we use this exponential growth function. We're going to write the formula just a little different when we talk about compounding continuously, but the things still mean the same thing. So in this case, A is the future value, P is the principal, the amount you invest, and R is the interest rate. It looks a lot like the other equation, we just replaced the letters a little bit. So we want to find the exponential function first. We know that we invested $15,000 at an interest rate of 5.4%. That means that P is going to be 15,000, and R is 5.4%, which as a decimal, 0.054. And so our function is just A equals 15,000 e to the 0.054 times t. And now if we want to determine the balance after 5 years, we're just going to let t be equal to 5. Right? So this is our function. We're going to let t be equal to 5 because it's been 5 years. And we get 15,000 e to the 0.054 times 5, which gives 0.27, which is 15,000 times 1.30996 Remember not to round till the end. I'm just rounding so I don't have to write all these numbers out. 19,649.47. And so after 5 years, the account should have $19,649.47. So, in some cases, we're interested in knowing how long it takes for something to double. Right? So if you invest $100, how long is it before you have $200? You invest $1,000, how long is it before you have $2,000? It's a good thing to know how long it's going to take for your money to double. So if we use that exponential growth equation, and we say that the future value is 2 times the initial amount, right, then what we get is that equation you see here in the middle. If we then divide both sides by the initial amount, we're left with 2 equals k times t. And then if we take the natural log of both sides, it's like we're solving this thing. We get the natural log of 2 is equal to k times t. And notice I've capitalized the t in that last equation. In this case, k represents the growth rate, and t is called the doubling time. It's the time that it takes for the amount to double. Notice that it has no basis on how much you invest. So if you invest $100, or if you invest $1,000, it's going to take the same amount of time for that money to double. So let's try this. Suppose you invest $4,000 at 7.2% interest. How long will it take for your money to double? Well, what we want to use is the doubling time equation. Natural log of 2 is equal to k times t. Well, the natural log of 2 is 0.69315. In this case, our growth rate is 7.2%, which is 0.072. And so k is 0.072 times t. And so to solve for t, we just divide. And you find that at 7.2% interest, compounded continuously, it would take 9.6 years for your money to double. Or almost 10 years for your money to double. It wouldn't matter if you invested $4,000 or $40,000. At that interest rate, it's going to take 10 years for your money to double. So, we could also talk about things being cut in half over time. Right? So one thing that's really relatable to this is when we talk about radioactive decay. Radioactive samples decay at a rate known as the half-life. So if we're looking for the time that it takes for a sample to decay in half, we want to have half the original amount. We can use a very similar formula, except now it's the natural log of 1/2 is equal to k times t. And when we're dealing with exponential functions, these types of formula will work for everything. If we were looking for the time it would take for money to triple, right? If we wanted the tripling time, we could say the natural log of 3 was equal to k times t. If we wanted to talk about quadrupling, it would be the natural log of 4, and so on. So, let's practice a few with half-life. A sample of lead has a half-life of 22.3 years, so that's the amount of time. We want to know the decay rate. Well, we know the natural log of 1/2 is equal to k times t. And the natural log of 1/2 is minus 0.63915. And that's going to be equal to k times 22.3. Because our half-life is now t. If we divide both sides by 22.3, we're going to find that K, I've kind of run out of room here, we're going to find that K is equal to 0.0311, or 3.11%. I'm sorry, it's negative 3.11%. This thing is decaying, so K should be negative. Krypton decays at a rate of 6.5% per year. Now we want to determine the half-life. Same equation, the natural log of 1/2 is equal to K times T. We know that the decay rate is negative 6.5% because it's decaying, it should be negative. And so that means negative 0.065. And so the natural log of 1/2 is negative 0.69315. K is negative 0.065 times T. We then just divide. And we're going to get T equals about 10.66 years. So that sample of krypton will decay in half in 10 years. Finally, the last thing we can really do, or the last thing we're really going to do with exponential functions, is talk about what's called a limited growth function. So a limited growth function is so named because it grows exponentially, but it's limited by the amount. So in other words, if we're talking about something like the spread of a disease, right, the spread of a disease, say, in a town, then the disease can only infect up to the population of the town. It's limited by the number of people that are there. That growth is limited. It may still be an exponential type of growth, but it's limited in its capacity, essentially. So a limited growth function has the form you see here. P of t is equal to a over 1 plus b e to the minus kt. Now, this equation's got a little bit more to it than what you're used to seeing. But what you really need to recognize is that a is what's known as the limiting value. Okay, that's the a, that number in the numerator, is the biggest the function could be. That's the most people that could get infected by the disease. So, let's try one of these. In a town whose population is 3,500, a disease creates an epidemic. The number of people n infected t days after the disease has begun is given by that function there. We want to find the number of people initially infected. So first we want t equals 0. So let's just start with that equation. I'm going to go to the next slide so I don't run out of room. And we have n of t is equal to 3,500 over 1 plus 19.9 e to the minus 0.6 t. So first we want the initial amount. How many people were sick to start off with? And that means t equals 0. And so that's 3,500 over 1 plus 19.9 e to the 0.06 times 0. And so negative 0.6 times 0 is just 0. And e to the 0 power is just going to be equal to 1. And so what we wind up with is 3,500 over 1 plus 19.9, which is 3,500 over 20.9, and we get 167. So 167 people were initially infected. Notice that number doesn't give you an exact value, but we're talking about people, and we can't have 0.4 or 0.5 of a person. So just round down to the nearest whole number. The actual answer there should be 167.5, right? But since we can't have 0.5 of a person, that just means that we had 167 who were initially infected. Now the second part of the question asks, find the number of people that are infected after 12 days. So now that means T is equal to 12. And so we're going to get 3,500 over 1 plus 19.9 e to the minus 0.06 or minus 0.6 times 12. Well, that's going to be 3,500 over 1 plus 19.9 times 0.6 times 12 is 7.2. So that's e to the minus 7.2. And so that's 3,500 over 1 plus 19.9 times 0.00075. So if we multiply this by 19.9 and then add 1, we get 3,500 over 1.0149. And we see that we have 3,448 who are now sick after 12 days. And so when you're dealing with these limited growth problems, the idea is just to plug in the values that you're given and be able to plug this into the calculator. And so finally, at the end of this lesson, you should be able to use exponential growth to model real-world data. You should be able to determine the doubling time and half-life given the growth or decay rate. You should be able to use limited exponential growth to model real-world data.